Hello and welcome to our video on balancing redox reactions. This is part of our redox reaction series. Alright, so this video is going to cover a little bit of a review on our redox terms from an earlier video. We're going to have a look at some half reactions again, as well as balancing half reactions. So having a look at some of the rules that we have to apply to balance half reactions, as well as using some worked examples to go through and try and understand the ins and outs to this. A little bit of a review of our redox terminology is going to be important as we move through the rest of this video. So some of the terms I need you to recall is oxidization, as well as reduction, and then our oxidizing agent and our reducing agent. And what I'm always going to call back to is our mnemonic oil rig, so we can define or find what's happening in our reactions. So just a quick recap, I'm going to give a reaction. So our copper plus iron and then plus our copper again. So when we look for oxidization, we look for something that is losing electrons. So in this reaction, let's have a look at what's happening to our copper. Copper plus is going to just copper itself as a solid. So here it is gained an electron because it's lost that positive charge. So we know it's reduced. And then on the other hand, we have our iron. And then it's going to Fe 3 plus. As a result, it's become positive because it's lost electrons. So oil rig, it's been oxidized. I want us to remember an oxidizing agent is a species that causes another species to be oxidized. So usually one way to think about it is what's reduced, the thing that accepts electrons or gains electrons, is the oxidizing agent. So our copper on this hand is taking away electrons or causes our iron to be oxidized. So that's going to be our oxidizing agent would be copper, and then the vice versa for our reducing agent. Following on from our terms, an important thing to know about balancing redox reactions is being able to identify our half reactions. So that comes down to looking for a species that's been oxidized, as well as looking for a species that's been reduced. So what I like to do with these half reactions is track one of our elements, for this instance, zinc. And so when I'm tracking zinc, I have a look at what it's like on our reactant side. So these two coincide. And then what I like to do is have a look at what it's like on our product side, as well as breaking it down into its other components. So here I've removed that sulfate region just to have a look at what zinc is as a charge. As well as with copper, I had a look at what copper was beforehand. And I know it's got a 2 plus because of the sulfate ion, and then following over to what it is as the products. So you know this reaction as a single displacement reaction between our metal. One other thing we've got to look at is also having a look at its oxidization state. So we looked at that in a previous video. We use our oxidization state to compare what an element was when it was a product. So here zinc is a 0, as well as when it's now, when zinc was a reactant, compared to when it is now as a product, where it's 2 plus. So it's increased, and as a result, an increase in oxidization state is loss of electrons. So it's oxidized. So some general tips moving into balancing half reactions is you're going to get a variety of different types of redox reactions that you need to balance. And the first step to balancing any redox reaction is identifying the half equations. And they follow as before. Follow some elements through, see what's being oxidized and see what's being reduced. Now moving forward, some tips for solving these redox reactions or having a look at these half reactions is have a look in your formula and data book that you've been supplied with. Your formula and data book is your Bible, and it will have a lot of your half reactions, even when you have a look at electrode potentials for your galvanic and electrolytic cells. So keep an eye out in your formula book for those half reactions. And again, look at that oxidization state across a reaction. So compare what it was when the element was a reactant to what it is now as a product. And always use oil rig as a mnemonic. It's a great way to just save yourself the hassle in noticing what is oxidized versus what is reduced. I think the best place for us to start is by having a look at a problem. The question we're looking at is write the equation for the redox reaction between iron and permanganate iron in an acidic solution. Now, I'm not going to expect you to know the name for specific ions like permanganate, so I will refer to it from this point forward as MnO4. The two things we know in this question is that it's a redox reaction between iron as well as our MnO4 negative. So we know that they're our reactants, so they're going to be on the left-hand side of our reaction. So I'm going to keep them split for now so you can see what our half reactions are. And then they're going to have, one of them's going to be reduced and one of them's going to be oxidized. Now, typically, iron will go from Fe2 plus to Fe3 plus, and our MnO4 is going to go to Mn2 plus. Now, I'm not going to expect you to know this, and this isn't typically expected for you to know whether or not their oxidization and their reduction reactions, because what I recommend is to look in your formula and data book and look for iron as well as for your MnO4. And what you'll find is these two formulas here. And one thing you can see is with these formulas, they're balanced. So our first step with solving a redox reaction or balancing a redox reaction is finding the half reactions. This you might be able to skip through and look in your workbook, the data book, and find these two half reactions here. Now, the next step for half reactions is balancing them individually. So we've noticed that in our data book, each one comes individually balanced, but we can't quite substitute each reaction into one another, which is our end goal, to have one formula for this. So before we substitute them into one another, we've got to balance the electrons across the two half reactions. So what we know in our MnO4 reaction, that is a reduction reaction. I'll write out oil rig. Reduction is gain. It's gaining an electron. We notice that we have 6 electrons in the reaction compared to our oxidization of iron, which has 1 electron, and it's on the right hand side in the products. So what we've got to do to balance the equation is we're going to multiply it by a common factor to get that up to 6. So this should be actually 6 here. Now that I've multiplied it by 6, so you can see down here it's multiplied by 6 and each are spread out. What we can do is now add our two half reactions together and cancel out the common terms. So What I do is I look across our two half reactions and have a look for our common terms. So right now we have 6 and 6 electrons. Here it's on the product side versus on the reactants over here, so that's going to cancel out. As well, I'm looking for if there's any water I can cancel out, which there isn't, as well as our hydrogens that I can cancel out, but it doesn't look like I can cancel any of those out. And then what happens is that will just carry down, and we can substitute this portion here, our reactant sides from the two, put them together like this, and the same goes for our product side. We'll just put those together minus what we can cancel out. And when we cancel out things, they cancel out if they're on opposite sides of our reaction. So here, this is on our reactants, it's on our products, so those two will cancel out one another. We will never have electrons left over because the goal is to always balance the electrons back in this earlier step, so we can cancel them out in this step over here. And that's how we balance a redox reaction. Now moving on to some more difficult redox reactions that we can balance, we're going to use the half equation method, which is similar to the previous method that we ran through. Now, not all syllabuses are going to require you to know this, but it's important nonetheless to have a little bit of an overview because there are some similar principles in this method that we used in the previous example. So the half equation method in acidic solutions, and we're going to see what we have to do in basic solutions. But the general rule is we're always going to start off with our two half reactions separated. And what we're going to do is we will balance the elements in the equations other than our oxygen and hydrogens. So we're going to neglect those in the first step and only worry about balancing everything else. From that point, after we've balanced those out, we'll then balance our oxygen atoms by adding the appropriate number of water molecules to the opposite side of the equation. So think if I have A and it goes to A positive and we have plus an oxygen over here, for this example, O2, we're going to add 2 H2O because that's going to give us our 2 oxygens on the right hand side. Now the next step would be to balance the hydrogen atoms, including the added ones in step 2. So since we added hydrogen atoms with our water, we're going to have to balance that out, and we're going to balance it on the opposite side. In this arbitrary example, I added 4 hydrogen, so I'm just going to add 4 hydrogen on our opposite side here. Let me clear that up. 4 hydrogens. Then from that point, we're going to add up the charges on each side, and we have to balance them by adding electrons to the more positive side. So right now, we have, again, this is an arbitrary example. This isn't going to be the truth for all of them, but we've got 4 hydrogen protons here, so that's 4 positive charges plus 1 here. So we have a total of 5 on this left-hand side, on the right-hand side, but on our left-hand side, we have a 0. So what we would do is on our right-hand side plus 5 electrons, because then that's going to balance the charge across the reaction. And the next step is the electrons on each side must be made equal across reactions. So now I'm going to go back a page so we can see that. This is this step here. So you can see our MnO4 half reaction in your book comes already balanced perfectly. Comes with adding the water, adding the hydrogen, and adding your electrons. But our iron, on the other hand, comes balanced as well, but we see that it doesn't have the same number of electrons across them originally. So that's why we have to balance it by multiplying one of our reactions by a common factor. And our common factor is 6. And that's what step 5 refers to. And then step 6, half equations are added together, cancelling out electrons and common terms. So that's this step here. So our final 2 steps are very similar to the previous example we looked at. And since we've looked at balancing them in acidic solutions, there's a slight variation in our rule to balancing them in basic solutions. So they're similar, but there's one difference in between step 3 and 4 in our previous example. We have something called 3b, and for that we're just going to add the appropriate number of OH to neutralize all our H+ and convert it into water molecules. So it's probably best to see this example in a worked example for our basic solutions. So we're going to jump into 2 worked examples now. Alright, so our first problem we're going to look at is a balancing redox in an acidic solution. So typical questions like this is you'll get a redox reaction and it wants you to balance the redox reaction either in an acidic or basic solution. For this one, we're going to do it in an acidic solution, so we're going to follow the steps previously outlined. We know the common thing between all our reactions is to find our half reactions between these. So I'm going to start off with my dichromate. And again, I don't expect you to know the names of these molecules, but we know our dichromate, because of the chromium, is going to go to a chromium here, and it's got a 3+. On the other hand, our other half reaction is going to be our nitrous acid. And that's going to our nitrate ion. So what I'm doing, same as before with all the previous half reactions, is just following through a couple of our elements. So I'm going to just follow through the chromium for our first half reaction and see where it's gone. And same for the nitrogen in this reaction going over to the nitrogen in our nitrate ion. Now the first step following our acidic reactions is balancing everything other than hydrogen and oxygen. We know what that's going to look like is we start off at the top, we've got 2 chromiums here, and we're not worrying about balancing our oxygen yet. We'll come to that later. And we've got 1 over here. So we need to balance this with a 2. So we've got 2. On the other hand, our nitrogens 1 and 1, they're already balanced. That's awesome. The following step now is we've got to balance the oxygen by adding our water into it. So to balance the oxygen, we have 7 over here. So what we're going to have to do is add 7 H2O. And so we've got 7 oxygens. On our other half reaction, we've got 3 oxygens on our right hand side compared to 1 oxygen on our left. So we've got to add 1 water, so we're going to get 1 hot oxygen. So I'm going to do H2O plus on this side. And we know that that's a liquid, and that's also a liquid, but we'll just leave that out for now. So now we've balanced our oxygens. Now it's time to balance our hydrogens by adding protons to, of course, the opposite side to balance it out. So let's have a look at our top here. We've got 14 hydrogens over here, 7 times 2, and we've got none on the other side. So we're going to have to add 14 hydrogens over here. And remember, our hydrogens have a positive charge. They're our protons that we're adding in our acidic solution. All right, let's do it to the second half reaction. Now it looks like we've got 3 over here and we've got none on our other side. So we're going to have to add another 3 hydrogens on our right hand side. I'll just get rid of these lines now. Okay, sweet. It looks like we've balanced our hydrogens. Now the next step we're going to move on to is balancing the charge across each equation with our electrons. So let's have an add up of our charge on our top equation. So we're looking at a 12 plus. I'm going to use a different color here, a 12 plus on the right hand side, on the left hand side, because we've got 14 positive protons and we've got a -2 charge here. So 14 minus 2 is going to leave us with 12 on the left hand side. Now on the right hand side, we've got 3 here, but it's multiplied by 2 because we've got 2 of the chromium. So we've got a 6 plus. Now we've got to balance them out. And since we're only balancing them by adding electrons, which are a negative charge, we're going to have to bring our left-hand side down. So to bring it down, we're going to add 6 electrons. So that will balance out our charge between the two. And we're going to do the same for this example. So we're going to look at what our charge on the right-hand side is and compare it to the left-hand side as well. So we've got no charge at all over here on the right-hand side, on the left-hand side. But on the right-hand side, we have 3 hydrogens, and we've also, or 3 protons, positive, and we've got a negative charge. So it's going to be a 2 plus. We know the net is 2 plus on the right-hand side. So we've got to get this down to match our other side, which is 0. So we're going to plus 2 electrons. So far, we've balanced the equation pretty well. The next step is we've got to bring them together. And to bring them together, we've got to balance the electrons across both our reactions. So we know in our top half reaction, we've got 6 electrons on the left-hand side, and our bottom, we've got 2 on the right-hand side. So they're not going to cancel one another out. So we need to do something to our bottom equation. So what we're going to do to cancel it out is we're going to look for a common factor between 6 and 2 to get that 2 up to 6 electrons. So we're going to just multiply this whole equation by 3. And what that's going to look like for us is 3, 3, 3, 9, 6. So now we've got the 2 here, 6 and 6, so they will cancel out. And the final step is just merging the 2 equations together and cancelling out the common factors. So for that, we're just going to have a look at it on another slide where it's a little bit neater. So here are our first steps we went through. Separate our half reactions, balance the elements other than the O and H, add our water to balance out the oxygens. So we're going to balance our hydrogens by adding the protons. So we're just looking, that's at 14 on the right hand side, so we're going to add 14 over here. Balancing the charge of electrons. So this is the big thing I kind of want to make sure everyone gets down pat, is to balance our electron charge. We're going to compare the two, so we know the 2 times 3 plus is going to give us a 6 plus on our right hand side, and we have, neglecting the 6 electrons right now, we have 14. We have 14 plus a 2 negative charge, so that's going to give us a 12 positive. So we're going to have to bring this 12 down to get it to 6 plus. And that's where these 6 electrons come from. And you do the same with your other half reaction. With that now, we're up to that final step where we have to scale the reaction so the electrons are equal across both reactions. Now the reason we get them equal across both reactions is so we can cancel them out when we bring the two reactions together. So we saw in the previous equation that we got to, or the step we got to, we had 2 electrons, and it is nowhere near the 6 electrons in our first half reaction. So to get it up to 6, we're going to just multiply it by 3. What we do is just expand it all out, like we did on the bottom here, and then we're just looking for common terms and cancelling them out and adding the 2 reactions together. So again, our common terms that we know we're cancelling out is our electrons. Now let's have a look at what happens to nitrous acid. That's just going to drop down. What I like to do is have a look at our hydrogens across the reactions. We have 14 on our left-hand side, and we have 9 here on our right-hand side. So what we're left with is going to be 5 over here on our left-hand side. So we're just going to do 14 minus 5. Sorry, 14 minus the 9 we have is going to equal 5. Because it's greater on our left-hand side, we're going to leave the 5 electrons on our left-hand side. Pull down the dichromate to here, and we'll do the same with our water. Let's have a look at our water. We have 3 on our left-hand side, and we have 7 on our right-hand side. So we're going to do the 7 minus the 3, and that's going to leave us with that 4. And we just carry down what we have left over if it can't be cancelled out or reduced. That's going to be our nitrate ion as well as our chromium. And that's how you balance the problem. One thing to remember for those kind of questions is it can be multi-layered, so it might get you to balance the redox reaction, but it might also ask you to identify what has been reduced and what has been oxidized, what is your reducing agent, and what is your oxidizing agent. So we've gone over those in a previous video, and so if you've used the flashcards and those ones, they will stay recurrent for you. But just always call back to oil rig if you ever get stuck when it comes to determining what's been reduced or what's been oxidized. Oil rig oxidization is loss, reduction is gain, and it's all in terms of electrons. Let's jump into our final problem for this video. So our final problem is balance the following redox reaction in basic conditions. So we know in basic conditions, we're going to have to do something slightly different to our acidic conditions, but it's only a minor change. But we're going to follow through the same steps pretty much majority of the way out, and I will flag where we get to, where we have to do something different. So again, we're always going to start off with finding our half reactions. So I'm just going to follow an element through. So we have our silver, and it is going to AgO, as well as we've got our zinc, which is 2 plus, going to zinc itself. So let's have a look at quickly what's been oxidized, what's been reduced from that previous statement. So, right, oil rig up here. So oxidization is loss. If anything's losing electrons, it's going to become more positive. We can't really tell up the top here for our silver straight off the bat without doing our oxidization states. But we can have a look at our zinc, and we know zinc is gaining electrons because it's lost that positive charge, so zinc has been reduced. Let's continue through with our half reaction. Let's balance our chemicals, our elements other than oxygen and hydrogen. So we know we're going to need 2 silver because we've got 2 over here. Everything else is already balanced. Now let's balance our oxygen across the reaction. We have 1 over here. In our first reaction on the right hand side, so we're going to add H2O on the left hand side. We've got nothing to balance in our second reaction, so we'll just leave it. The next one is we want to balance hydrogen with protons. So we've got 2 hydrogens in our first reaction on the left hand side, none on the right hand side, so to balance it, we're going to add plus 2 H pluses. Sweet. Our second reaction on the other hand, quite empty, makes it life easy. Now we're up to that following step, now balancing the charge with electrons. Let's have a comparison of our charges across. Right now we've got, in our first reaction, 2 hydrogen protons, so it's a positive 2 charge on the right hand side of our equation. So I'll just write right hand side, left hand side. We have +2 charge, and here's 0. So we've got to get that +2 charge down to 0, so we're going to add 2 electrons. And to get it gets it down because electrons are negative and we'll cancel out our 2 positive charge. On the other hand, our second equation, we've got a +2 charge on the left-hand side, 0 over here on the right. So we're just going to plus 2 electrons on the left-hand side. So right now we're at the very same step that we were in the previous example, but now we've got to just scale the 2 reactions. So right now looks like we don't have to do any scaling between the 2 reactions because our electrons are equal, and so we'll carry them through and we can substitute the 2 reactions into one another and cancel out any of the common terms. So I'm going to jump to that. There's that first step we're doing, second step, third, balancing with hydrogen. So sometimes I'll call back to an earlier example where you were looking, where I told you guys some of the solutions will be, or the half reactions will already be balanced in your workbook, so keep an eye out for that. And this is the step we were just at. Now, following step is to balance and add the reactions. We don't need to balance because the 2 electrons are fine. They're going to cancel one another out. And here we've balanced it and we've added the 2 reactions, cancelling out any terms. This one, unfortunately, the only terms we had to cancel out were the electrons. We didn't have anything else to cancel out. Let's jump over to the next step. Now, this is where our balancing in a basic solution is going to become a little bit more different from our balancing in an acidic solution. Right now, we'd be at the solution if it was an acidic one, but because it's basic, we're going to have to add any OHs to balance out our hydrogen protons. So we see we have 2 hydrogen protons on our right-hand side, so we're going to balance that out with 2 OHs, and because we're adding it to the right-hand side, we're also going to add it to our left-hand side. And as a result, any of our OHs and hydrogen protons, what's going to happen to those is they're going to produce water. So since we had on our right-hand side 2 hydrogens and we've added 2 OHs, they're going to come together to get our 2 H2O, and we're going to still leave our 2 AOH here on the left-hand side. And then what will happen is we continue, we'll check if we've got any terms that we need to cancel out. And fortunately for us, we've got water as well on that left-hand side that it will cancel out and become 1 water because we're just doing 2 minus 1. And the one that's left over is on the right-hand side of our equation. So that's how we balance in basic conditions. Remember, you might not have to get to this level of difficulty for the questions because the half reactions might already be balanced in your workbook or data books. So the steps that you'll want to follow is by balancing the electrons between the 2 and bringing them up to a common number. Now, some notes for that is, have a look for what's been oxidized and reduced, because questions will also ask that. They might be multi-layered. And always have a check in your formula book and data book for the half reactions because they might be there and it can save a lot of time under exam conditions.